Hi folks, welcome back to Math with Captain Rod. I'm making this video here to provide examples of how to write formulas for area under curves using different, I'll call them rectangle schemes here. So what we're going to do is we're going to go through three examples. In all examples we're going to be talking about the function y equals x cubed plus 1. I did a quick sketch here. Here it is here for example 1, example 2, example 3. And what we're going to do is we're going to write formulas for estimates of the area under that curve from 0 to 4 using LEP stands for left endpoints, this one stands for right endpoints, and this one stands for midpoint. Or if you've seen some of my other videos, I tend to call this the Goldilocks Method. All right, so let's get started. So I've already drawn the rectangles here to save a little video time. Using a left endpoint, meaning that the rectangle here is touching the curve on the left end, that first rectangle would look like this. The height is equal to the function value at x equals 0. The width is delta x. I'm going to go ahead and get the delta x. Now delta x are always equal to b minus a over n, where b is the upper bound, a is the lower bound, n is the number of rectangles. In this case, the b is 4, the a is 0, and we're dividing this into 4 rectangles. So we're going to have a delta x of 4 over 4, which is 1 for every one of these examples. That's a 4 here. All right, so the area of this first rectangle is f of 0 times delta x. The area of the second rectangle here, now we need this value right here. That's going to be equal to 1. Now, in a more general sense here, you'll notice that this is 1 times delta x. We're going to need that x value to get that function value for the second rectangle. Here we're going to need this one right here. We need this x value to get this length, that function value for this one's area, and then we're going to need this one, this x value. So what I'm going to do here is write a little formula for x, what I'm going to call x sub I. Because what we're going to do is we're going to write this as a sum from I equals 1 to 4. And I need a formula here that stands for the area. Now, whether you call this I equals 1 or k equals 1, that doesn't matter. That's just a name. This is just referred to as a dummy variable here. Now, you'll notice that for our first rectangle here, the x value you need is 0. And notice that for our second rectangle, the x value we need is delta x. And then third, it's 2 delta x. And fourth, it's 3 delta x. So x sub I believe, if we take I minus 1 times delta x, we're going to get a formula that's going to give us the correct x values everywhere. And I'm going to try it real quick. For I equals 1, first rectangle, 1 minus 1 is 0. That gives us this one. For the second rectangle, I is 2. 2 minus 1 times delta x gives me that one, and so forth. Okay, now keep in mind that our delta x is equal to 1. So the area of the ith rectangle, and I want a formula that's good for any one of these, is going to equal the function value evaluated at the x sub I times delta x. So the function is equal to x cubed plus 1. So what this thing is going to look like is x sub I. It's going to be I minus 1 times delta x cubed plus 1. Now that gives me the length of each rectangle. Then don't forget, you still have to multiply by the width, which is delta x. So here is a formula that will estimate, give me an approximate area under this curve, x cubed plus 1, breaking it into 4 rectangles. This formula is going to give us what's called a lower bound estimate. You'll notice that it's missing these little pieces here, 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 and here. So it's going to give me something just a little short of the area. And again, I could recopy it with the delta x of 1. I'm going to leave it like this, though, because I like these. You know, if we put the 1 in, you're going to kind of lose the dimensionality, if you will, of this equation here. This is a length times a width gives an area. And again, the length here in this example is defined by the function values at this location, this location, this one, and this one. All right, let's move over here and talk about this one, where we're using right endpoints. So now The x values I need, I'll put green highlights here. You know, this was the first one, second one, third one, fourth one. All right, now the first x value I need is here at 1 delta x. The next one I need is here at 2 delta x, and then 3 delta x, and then 4 delta x. So my formula for the x sub I think if we use I times delta x, that will give me the correct x values we need. So for example, here's 1, 2, 3, 4. Let's say the third rectangle. 3 times delta x puts me exactly right there, so we're good. All right, so our area, if I write a formula for the a sub I, that's going to equal the function value at x sub I times delta x. Total area estimate is going to be the sum, so I'm going to put area approximately equal to the sum from I equals 1 to 4. Okay, f of x sub I, same function here, so that is going to be I times delta x cubed plus 1. And then to make it an area, we got to multiply it by delta x. The delta x is the same as it is in this example. It's 1, but I'm going to go ahead and leave this formula just like this. All right, now you'll notice that here the rectangles are including areas that aren't actually under the curves. So this one's going to give us an upper bound estimate, a number that's just a little bit too big. All right, third. Now we're going to use the midpoint rule, and I wish this picture would have came out better, but this rectangle, you can see it goes through the midpoint very clearly. This is supposed to be a midpoint. Sorry about that. That one's pretty good, right at the midpoint, and again, midpoint. So the x values we need, I'm going to put them in green. We need this one right at the midpoint of the rectangle. That's here. The next x value we would need is this one, middle of the rectangle, middle of the rectangle, middle of the rectangle. So the first thing I'm going to do is try to write myself a formula for the x sub i's, the x coordinates at these green marks. Do this over to the right. Now, look at the previous one we had, the I times delta x. I'm going to start with that. This I times delta x puts you at the right-hand side of each rectangle. So for example, here's the second rectangle. If I put I equals 2 in, 2 times delta x puts us right there. But we want to be just to the left of that. So if we subtract 0.5 times delta x, there is a formula that will get us to the left-hand side of every rectangle. Watch. Look at the fourth one. 4 delta x's puts us here, right? 4 times delta x, that would put us right there. Subtract 0.5 delta x puts us right there. So here's a formula here. We could write it different ways. I like to just leave it like this, but you know, if you wanted to, we could write this. Well, we could factor the delta x out and write this I minus 1/2 times delta x. That's the same thing. All right, now write a formula for the a sub I, which stands for the area of the ith rectangle, whatever one we want. And that's going to equal f of x sub I times delta x. And that's going to equal this cubed plus 1 times delta x. I need a little room here to write that out. So that's going to be, again, pardon me here. Let's see, I minus 1/2 times delta x cubed plus 1. I need another parenthesis here. I'll use these guys. Times delta x. So this formula here gives me the area of the whatever rectangle I want, the first one, second one, third one, fourth one. So a formula for the total area, we're going to say the total area is approximately equal to the sum, I equals 1 to 4, of this expression. And I don't feel like recopying that, so I am going to cheat. There we go. All right, so again, this video was about how to set up the formulas. That's very, very important in the study of calculus and numerical methods in general. This type of math is really critical to understanding calculus in general. So again, this one gives us a lower bound estimate because we're missing, oops, use my pointer here, because we're missing little areas. This type of setup gives you an upper bound estimate. This one probably gives you the best estimate because, you know, here we're overestimating, but here we're under, over, under, over, under. I like to call this the Goldilocks method. You know, this gets you an answer that's a little too big. This gets you an answer that's a little too small. This gets you the answer that's just right. Now, some things to consider moving ahead. So when you're trying to calculate an area numerically, you know, here we're using just 4 rectangles. If you had to use a calculator or something, that would be an appropriate type of thing. But if you bring in a computer, like I like to use Microsoft Excel, you would typically bump this to a larger number of rectangles. I like to use 10. That's a nice round number to use for this. And that tends to give you pretty good estimates. You can get within less than, you know, most of the time, less than 1 or 2% with just 10 rectangles. But with something like Excel, it's really easy to bump this to 20, 30, 40. And what happens is the difference between these methods gets smaller and smaller and smaller. When I do numerical calculations, I almost always start with this formulation. But down the road, too, when you're talking about a bit more abstract mathematics, and you're talking about, when we start talking about introduction to integration, and this, by the way, is integration. I guess what I meant was using integrals to find these areas and finding exact solutions. What you'll be doing down the road is driving n to infinity using the limit process. And it turns out that when you're going to use an infinite number of rectangles, you can use any of these 3, and all 3 will converge to the same answer. So anyway, this is just meant to be kind of an introductory video on how to set up formulas for, you know, finite formulas, you know, in this case sum from I equals 1 to 4, for area under the curves using different rectangle schemes. The pictures are very, very important. Make sure you draw good pictures and be very clear about how you're setting up the rectangles. In your picture, I would put little dots on the x values you need, so that will help you write a formula for what I call the x of i's, the x values you need for each rectangle. Write a formula for the area of each rectangle. Insert that formula into a summation, and you're done. Right? As far as writing the formula here, then you would normally use a calculator or a computer to compute values. So I hope that this video helps. Have a great day.